Hi everybody, now it's time for an exercise, okay? So, we have Espresso House is testing two types of ads to promote its new höstlatte, okay? And version A includes the price of the latte and version B does not. So, which is more effective for increasing sales of höstlatte? And here we have to consider the following approaches for comparisons. Explain whether the approach is contaminated by confounding. Okay, so we learned about confounding in the previous video, right? If so, identify a possible confounding or lurking variable. So we have three studies here, and version A is used at a store in Bergen and version B in Oslo. Okay, so is there a confounding variable? So take 5 seconds, okay, and think about it. Okay, so one obvious confounding variable here is the difference in location. So you have confounding based on difference in location. Okay, so it might be such that customers in Bergen have different preferences than customers in Oslo, or that the store layout in Bergen is different from Oslo, and so you never know. So you can't really say that the effect of a difference in means is because of the price reveal of latte. Okay, so and scenario B is that version A is used on Mondays at a store in Oslo and version B is used on Fridays at the same store. Take 5 seconds to find the confounding variable. Okay, so here it's obvious that there is a difference in between the groups because one group is taken from Mondays and another group is taken from Fridays. So yes, we do have confounding based on weekday. So it might be such that the customers on Mondays are different from customers on Fridays. Maybe customers on Fridays are very youthful. You need some energy to party on during the weekend, or the old people on Mondays, they need energy for work or something. I don't know, but there's confounding. Okay, and scenario C, the höstlatte advertisement is sent by mail to people living in Oslo. Version B was sent to randomly selected set of people, and the same is done for version B. Okay, take 5 seconds. Okay, so here you actually have randomization, and that is very good, very good. So no confounding. And let's see if I can do this and just make it look better. So okay, so you have no confounding, but yeah, so from people in Oslo, you are quite certain if the sample size is large enough, then you're quite certain that any difference between version A and version B is because of the inclusion of the price. Okay. But can you use it? Okay. Does it have external validity? It does have internal validity, but it might not have external validity. Okay, might not have external validity. Okay, and what does that mean? It means that can you generalize this result to the population? Yes, you can, but the population is really not what you're after. You're after the customers of Espresso House. Okay, so you have to have that in mind. So so maybe you should send the Höstlotte advertisement to customers. Okay, customers of Espresso House. Okay, a bit of voice crack there. So we are using data from an experiment or A/B test to compare sample averages. Okay, because experiment and A/B testing is very efficient to get the cause and effect of something. Okay, so what we do is we want to assess the difference between sample averages. Okay, between this sample and this sample, the test sample and the control sample. Okay, so we want to know if it's statistically significant, and then we can use a two-sample t-test. Okay, so a two-sample t-test is really quite similar to the one-sample t-test, but the two-sample t-test tests the difference here. This is just the sample average of group 1, and this is the sample average of group 2. Okay, group 2, and what you see here is this D naught is like a cutoff, and this is just for the hypothesis test. And why do you have that cutoff? Well, it means that you want this difference to be greater than this cutoff. Okay, often this cutoff is set to 0, and then you just test is this difference greater than 0, right? But if you want this difference to be something else than 0, just 0, before you take action, then you penalize this difference. Okay, it's much better when we put numbers into the equation, and this is kind of normalized based on the standard error. Okay, so this is the standard error of the difference in means. Okay, so what do you have to check? Well, you have to check if the sample size is large enough, okay? And you have to test both groups, both group 1 and 2, okay? So if this n, the sample size is, for example, n1 is greater than 10 times the kurtosis from group 1, so you just take the whole sample, you calculate the kurtosis of that sample, of the x, and you take the absolute value of the kurtosis times 10, and if the sample size in group 1 is greater than that number, then you have a large enough sample size, okay? So, and you have to check degrees of freedom, because degrees of freedom, it decides the cutoff value for the t test. So the degrees of freedom plus the significance level decides the critical value for the t. Okay. We'll get back to that, the testing, but you can use a rule of thumb, because if you look at a t-test for a mean, for one mean, not a difference in mean, but one mean, then the degrees of freedom would be the sample size minus 2, right? But you can use that the degrees of freedom is sample size group 1 plus sample size group 2 minus 2. But only if the variance of the two groups are similar, okay? So then you would have to calculate the sample variance of the two groups. So it's of course better to use a statistical software to do this, and often you get this automatically. So what can we say about comparing differences? So, well, you have the population parameter, okay? So these are the observables, okay? And this is the mean, or the average, the population average, okay? So this is the population average of group 2, 1 and 2, I mean. Okay, and what is your null hypothesis? Well, the null hypothesis is, if this is true, or if this is not rejected, then you do nothing, okay? You do nothing. So you do nothing if the difference between group 1 and group 2 is less than or equal to a certain cutoff value, okay? So if you want to do something, how can I explain it? Well, if this is true, or if you find this, then you do nothing. But if you find this, if this is true, the difference between the average of population group 1 minus population group 2 is greater than the cutoff, then you reject the null hypothesis and you keep the alternative hypothesis, and then you take action, okay? Because the first group here got the treatment, okay? So then you give treatment to the whole population. And this cutoff, it might be 0 or it might be a positive number, okay? It really depends on how expensive it is to give the treatment to all instances in the population, and how profitable it is for those to get the treatment, okay? So it's just like a cost-benefit analysis you have to do. And the sample statistic, because these are not observable, you have to calculate the sample average, okay? These are sample averages. And you look at the difference between the two samples, the two sample means, okay? And this estimated standard error is the standard error of the difference in mean. And here you can use the sample variance. Okay, so the sample variance, you can just calculate the sample variance for each group, and you divide them by their respective sample sizes, okay? You add them and take the square root. Then you get the standard error of the difference in mean. So this is observable, and this is observable. So then you can calculate the test statistic, which measures how far away from the cutoff. This is the distance of x1 minus x2 penalized by a cutoff divided by the standard error. So in standard error units, how large is this difference, okay? And then you get the t-value. The statistical program will also get you give you the p-value, and if this p-value is greater, oh no, sorry, lower than the significance level. This is the significance level. And it's often 5% or 0.05. They are identical. Then you reject, if this is true, the p-value is less than the significance level, or the t-value here is greater than the critical t-value. Then you reject H0 because the difference in means is so great in standard error units that it's highly unlikely that H0 is true. Okay. So and this critical t-value is found by looking at your significance level and and your sample size, okay? Or the degrees of freedom, I should say. Okay. So what we have is we continue with the cookie cats example, and you should make an A/B test, okay, to decide whether they should move the first gate to level 30 from 40, okay. So you conduct an A/B test. So you have a sample of 90,189 new players who downloaded the app, and these were randomly assigned to version A or to version B, okay? Randomization, hugely important. And so 44,700 players got version A. That's with the new version, okay? Version A is the new version, it's level 30. And 45,589 players got version B, which is the old version, okay? So already you know that a change is a change from level 40 to level 30, okay? So you know which group is group 1 and which group is group 2, right? So those who got version A, they are in the first group. So here you want to calculate a sample mean, and version B, they are in the second group, because you want to know if version A, the new version, is better than the old version, right? So if you have some descriptive statistics, or you put the data in your program, you run the commands, and you get the descriptive statistics. So here you have the group with level 30 and the group with the gate at level 40, and you have the sample size. This is the n. You have the mean, that's the x bar, and you have the standard deviation, that would be the s, okay, and you have the kurtosis, which is the k4. Okay, so now you have a lot of numbers, and the way you find these numbers is just that if you have a table, oh my gosh, that's really skewed. Okay, if you have a number, okay, that's it, okay. So you have player 1 and player 2, etc. And so this is players, and often these are just numbers, okay, number IDs. And then you have a version, and that would be, for example, player 1 was assigned gate 30, which is the new gate, okay, the new version, and player 2 was assigned gate 40, okay. And then you have the number of rounds, and maybe player 1 played 143 rounds and player 2 played 22 rounds, okay, during that 14-day period after installing the game, okay. And then you can just this is the sample size is just to count everyone at gate 30 and every player at gate 40, or assigned to gate 40, and add up. the mean is the mean rounds. Okay, so this is the mean rounds. Okay, and this is just the sample sample standard deviation of number of rounds, okay, for each group. And this is the kurtosis of the x variable, the number of rounds, okay? So, then in Stata, you can just use these commands, okay, summarize command, and get the above result. So it's super easy. So the question is this difference that's statistically significant? And we will look into that in the next video.